A particle crosses the dark and slams into Earth from a place that looks empty. Its trail points toward a giant hole in the nearby universe where almost nothing should be there. The maps say silence. The detectors say impact. And right now, the clash between sky and data is still not fully explained. If stories like this are exactly why you stare at the night sky, stay close. Subscribe for real space mysteries told in simple words, without the fake drama. Because this one gets stranger the deeper you go. Most things that hit Earth from space are easy to picture. A rock burns up and becomes a meteor. A chunk of ice grows a tail and becomes a comet. But cosmic rays are different, and that name can fool you. A cosmic ray is not really a ray, like a beam from a flashlight. Most of the time, it is a tiny charged particle, often a proton, which is the small positive part inside an atom. Sometimes, it is the center of a heavier atom instead. It races through space so fast that when it hits our air, the sky reacts. That reaction is violent, even though the thing that starts it is unbelievably small. The particle crashes into atoms high in the atmosphere. That first hit creates more particles, and those hit more atoms, and then even more, like a chain of falling dominoes. By the time the storm reaches the ground, one tiny visitor has become a giant shower spread over miles. Scientists have studied cosmic rays for more than 100 years. Most of them are strong, but not shocking. They come from the sun, from exploding stars, and from other rough and wild places in space. They are strange, yes, but usually they still fit inside the rules. Then one event broke that comfort. On October 15th, 1991, a detector in Utah saw a cosmic ray with so much energy that scientists gave it a name people still remember. They called it the "Oh my God" particle. That was not a joke name from the internet. That was how stunned people were. The reason for the shock was simple. Nothing in our own galaxy seemed powerful enough to make it. And if it came from far beyond our galaxy, theory said it should lose too much energy before reaching Earth. In plain words, the particle looked too strong to be real and too far traveled to survive. Still, it was real enough to show up in the data. Years passed, and that 1991 event stayed almost alone, like a single footprint on a clean floor. Scientists waited for something else like it. They built better tools, watched more sky, and kept asking the same hard question. That brings us to the West Desert of Utah. Out there, far from bright city lights, sits a huge experiment called the Telescope Array. It is run by an international team, including the University of Utah and the University of Tokyo. And it watches for the giant air showers that cosmic rays create above Earth. The telescope array is not one telescope in the normal sense. It is a wide field of instruments spread across the ground. More than 500 surface detector stations sit in a giant grid across about 700 square kilometers, or roughly 270 square miles. That is a huge listening net for very rare impacts from deep space. Each station waits for signs that a particle shower has reached the ground. By comparing which stations light up and when, scientists can rebuild the path of the original particle. They can estimate the direction it came from. They can also estimate how much energy that original particle carried into Earth's atmosphere. And then, on May 27th, 2021, something arrived. A single cosmic ray hit Earth with an energy of about 244 exa-electron volts. That is 244 quintillion electron volts. And a quintillion is a 1 followed by 18 zeros. For one tiny particle, that is an absurd amount of energy. The event set off 23 detectors in the array. The shower spread across about 48 square kilometers, or around 18.5 square miles. The team later gave the particle a name from Japanese mythology, Amaterasu, the sun goddess. And from that moment on, the old mystery had company. Here is why that matters so much. This was not just another strong cosmic ray. It was the second highest energy cosmic ray ever detected, behind only the 1991 Oh my God particle. So now scientists had not one impossible seeming event, but two. At first, that sounds helpful. If you have two events, maybe the pattern becomes clear. Maybe they come from the same kind of object. Maybe they point back to the same dangerous part of the universe. But this is where the story turns. When researchers traced the path of the Amaterasu event back across the sky, it seemed to point toward the local void. That is a nearby region of space with very few galaxies in it. It is not perfectly empty, but compared with other regions, it is like a cosmic desert. The local void sits close to our own neighborhood of galaxies. Astronomers have mapped it for years. Think of the universe as a kind of web, with galaxy clusters along bright threads and emptier spaces between them. A void is one of those emptier spaces, and this one is right next door in cosmic terms. Now think about what scientists expected. A particle this energetic should come from something extreme, maybe a giant black hole blasting out jets. Maybe a violently active galaxy with matter falling inward and energy shooting outward. Maybe some other engine powerful enough to fling matter close to the speed of light. Instead, the line seemed to point toward a place that looked like almost nothing. No obvious monster black hole, no clear blazing source, no simple target in the direction where such a particle should have been born. That gap between expectation and reality is the heart of the mystery. And it gets even harder. Very high energy cosmic rays are charged, so magnetic fields can bend their paths. But the more energy they have, the less they should bend. At these extreme energies, scientists expect only small deflections, small turns, not wild curves. So the original hope was almost like this. See the particle, trace its line, find the launcher. Not perfectly, but close enough. That is why these rare particles are so valuable. They might point us straight back to the most violent machines in the universe. Amaterasu did not play by that script. Its energy was so high that the path should have been close to straight. Yet when researchers looked where it seemed to come from, there was no clear source waiting for them. The sky offered the direction, but not the answer. That is like finding a bullet in a wall and tracing it back to an empty field. Did you know the universe can throw one tiny particle at Earth with more punch than anything humans can build? If that fact just stopped you cold, hit like and tell me what kind of source you think could launch it. And if you want more space stories where the data refuses to behave, subscribe and stay with me. To feel how wild this is, it helps to compare it with human machines. The Large Hadron Collider, the famous particle accelerator near Geneva, is the most powerful one we have ever built. Its particles are incredibly fast and incredibly energetic. But Amaterasu carried tens of millions of times more energy than those machine-made particles. Scientists even use everyday comparisons because the raw numbers are hard to feel. One description says, this single particle carried about the energy of dropping a brick on your toe from waist height. Another comparison makes it like the motion energy of a fast tennis ball. That sounds almost funny until you remember all of that energy is packed into one subatomic particle. Here comes the key rule that makes the case so strange. Researchers have long expected an upper limit for how energetic distant cosmic ray protons can be when they arrive here. This is called the GZK cutoff. The name is technical, but the idea is simple. Space is not truly empty. It is filled with faint leftover light from the early universe, called the cosmic microwave background. If an ultra-energetic proton travels a very long distance, it should interact with that background light and lose energy. So by the time it reaches us, it should be weaker than a certain limit. In other words, the universe itself should slow these particles down. That was the expectation. But the strongest events, like the oh my god particle and Amaterasu, sit above that expected ceiling. So either the source is closer than it looks, the path is stranger than we think, or part of the rulebook is incomplete. Scientists did not jump to wild claims right away. First, they checked the boring possibilities. Could the energy estimate be wrong? Could the detectors have misread the shower? Could the reconstruction of the direction be off by enough to hide a normal source? That careful work matters more than people think. Big mysteries are not solved by shouting about them. They are solved by trying to break your own result first. The telescope array team spent time testing the event, comparing methods, and asking whether something ordinary could explain it. So far, the event has held up. The 2023 paper in Science reported the energy at about 244 exa-electron volts. The team said the arrival direction still did not line up with any known object that looked strong enough to produce it. And that is why the mystery became bigger, not smaller, after publication. They also had another reason to take it seriously. The 1991 oh my god particle had been detected using a different method. So now, two separate kinds of observations across decades had found extremely high energy events. That makes it much harder to dismiss the whole thing as a one-time mistake. Now comes the part people remember most. If the line really points toward the local void, maybe the particle did not come from where it seems to come from at all. Maybe magnetic fields bent it more than expected. That sounds simple, but it immediately opens new problems. If magnetic fields are stronger or messier than current models say, then our maps of cosmic ray travel are incomplete. That would matter far beyond one strange particle. It would mean many attempts to trace cosmic rays back to their homes could be less reliable than hoped. The sky would be speaking, but through a badly warped mirror. There is another option. Maybe the particle was not a proton. Maybe it was something heavier, like the nucleus of a larger atom. Heavier particles carry more charge, and more charge means more bending in magnetic fields. So a heavier particle could seem to come from a place that is not really its birthplace. That sounds promising, but it comes with trade-offs. A heavier particle can bend more, yes, but it also changes how scientists think about survival, energy loss, and where such a particle could be made. You fix one part of the puzzle, and a new one appears next to it. That is why this case has stayed alive. And there is still another layer. The Amaterasu event and the 1991 event do not even point back to the same patch of sky. If there were one hidden source causing both, that would be a neat story. But the sky does not seem to offer that neat story. Instead, it suggests either several unknown sources or something deeper that links them. So, what did scientists originally expect? Rare, yes, but explainable. Violent source, mostly straight path, clear, rough direction. What did they actually find? Extreme energy, unclear source, and sky positions that do not make ordinary sense. Why does that gap matter? Because the most energetic particles are not just random fireworks. They test the limits of what the universe can build. If we do not know where they come from, then we may not understand the strongest natural accelerators in existence. That is a serious blind spot in modern astrophysics. What is your best guess so far? Hidden source, stronger magnetic fields, or some particle we do not fully understand yet? Drop your answer in the comments and tap like if you want more mysteries where one measurement changes the whole picture. And if you enjoy asking the hard version of the question, subscribe now. To be fair, scientists are not just standing still and staring at the same sky map. They keep building better ways to test the direction. They run simulations, which are computer-made models of how particles move through space, and they compare many possible paths instead of trusting one simple straight line. A later study brought in a new idea. Instead of assuming the particle really came from the local void itself, researchers asked whether its true source might sit in a broader nearby region. In plain terms, maybe the path had been bent just enough to mislead us. Maybe the line on the map needed context, not blind trust. Some of that later work pointed to possible source candidates outside the empty-looking region. One name that came up was MED-2, also called the Cigar Galaxy. It sits about 12 million light-years from Earth and is known as a star-forming galaxy, a place where many new stars are being born. That kind of place can be violent and energetic. Now, this does not mean the mystery is solved. A candidate is not a confession. M82 is interesting because it is active, nearby on cosmic scales, and not sitting inside an obvious nothingness. But linking one single particle to one exact galaxy is still extremely hard. These events are rare and the universe is messy. The methods behind that study also matter. Researchers used advanced simulations and modern statistical tools to test many possible paths. That sounds dry, but here is the simple version. They tried to let the data speak through many realistic versions of the cosmic journey instead of forcing one clean answer. That matters because cosmic rays do not carry little return addresses. We never see a tag that says, made in galaxy number 3. We only see the final crash at Earth and the shower that follows. Everything before that has to be rebuilt from physics, math, sky maps, and a lot of careful doubt. So the story shifted. At first, it looked like a particle from nowhere. Later, it looked more like a particle from somewhere that had been hidden by the trip itself. That is a softer mystery than a particle born in a true cosmic void. But it is still a mystery, because even if M82 or some other nearby galaxy is involved, we still need to explain the acceleration. What engine inside that galaxy could push a particle to this level? Was it a supermassive black hole? A violent burst tied to starbirth and death? Or something even more extreme? Here is where the tone changes from what happened to what is happening. Right now, scientists are still collecting events, still updating models, and still arguing over the best explanation. Amaterasu is not a closed case in a museum. It is an active problem sitting on the desk. If this is the first time you're hearing that a particle may have looked like it came from empty space, does that change how you see the universe? Leave a comment with the moment that surprised you most, and subscribe if you want the follow-up when the picture gets clearer. Because this story is still moving. Then came another major idea, and this one pushed the mystery into even stranger territory. A 2026 study suggested that some of the highest energy cosmic rays might be ultra-heavy nuclei. That means the compact centers of atoms heavier than iron. Not slightly heavy, extremely heavy. Why would that help? Because according to those calculations, ultra-heavy nuclei may lose energy more slowly than protons or medium-mass nuclei while crossing intergalactic space. If that is true, then some particles could survive much longer journeys without fading as much as expected. That would change the source hunt in a big way. Remember the original problem? Scientists expected that very energetic protons from far away would run into the microwave glow of the universe and bleed energy. That is why the GZK cutoff exists. But if some of the strongest events are not protons at all, the old expectation does not apply in the same simple way. The 2026 work did not say every ultra-high energy cosmic ray must be ultra-heavy. It said some of the most extreme ones might be. That is an important difference. Scientists are not tossing out the entire field. They are testing whether a special class of events needs a special class of particles. And if that idea is right, the list of possible birthplaces changes. The study pointed toward some of the most violent events in the cosmos. Things like neutron star mergers, where two crushed dead stars collide, or collapsing massive stars that may create black holes and huge bursts of energy. These are not gentle environments. A neutron star is already one of the densest objects in the universe. Mash two together, and the result is chaos, gravity, heat, and magnetic violence on an almost impossible scale. If nature is going to build an ultra-heavy cosmic bullet, places like that are high on the list. There was also another hint buried in that work. Researchers noted that a heavy contribution at the highest energies might help explain possible differences between what northern sky and southern sky observatories see. That is subtle, but important. When two parts of the sky do not behave the same, the pattern may be telling us something real. Still, even this idea does not close the case. A heavier particle would bend more in magnetic fields, which helps with the direction problem. But then you must show where such particles are made, how many should exist, and whether future detectors actually see the heavy composition you predict. A good idea is only the start of the proof. This is why Amaterasu matters so much right now. It forces several explanations to compete at the same time. Maybe the source is nearer than it first seemed. Maybe magnetic fields are shaping the path more than we thought. Maybe the particle type itself is different from the usual guess. And beneath all of those options is a deeper tension. Every fix changes more than one thing. You do not just explain one weird point on a sky map. You change how we read cosmic rays in general. That is why researchers are careful and why the answer cannot be rushed. What would surprise you more? Learning the source is hidden in plain sight, or learning the particle itself was something much heavier than expected? Tell me below, and if you like science stories where each answer creates a new question, hit like and subscribe for the next one. This mystery is still unfolding. The search is also getting bigger on the ground. The telescope array has been expanding with hundreds of new detectors planned to widen the area it can sample. The goal is simple. Catch more rare events, because one mystery is interesting, but a pattern is powerful. More detections would help in several ways at once. If many future events point near similar regions, that is a clue. If their energy is grouped in a certain range, that is another clue. And if their shower patterns suggest lighter or heavier particles, scientists can begin separating good ideas from bad ones. Other observatories matter too. In the southern hemisphere, the Pierre Auger Observatory in Argentina studies ultra-high energy cosmic rays on a vast scale. Future upgrades and future projects may sharpen the composition question. They may also help test whether the strongest events really come from the same types of sources in both halves of the sky. This is one reason the mystery feels alive instead of frozen. New data can still change the whole story. A single extra event will not solve everything, but a handful of well-measured events could begin to show whether Amaterasu was a weird outlier or part of a hidden population we are only starting to notice. Now step back for a second and look at the bigger picture. For years, the dream has been to use the highest energy cosmic rays as arrows pointing back to the universe's most violent engines. If those arrows are bent or mislabeled or made of stranger stuff than expected, then the map of extreme space is harder to read than we hoped. That is both frustrating and exciting. It is frustrating because science likes clean paths from evidence to cause. But it is exciting because this is how fields move forward. A result shows up that refuses to fit. People test it, fight over it, refine it, and slowly build a better view of reality. Amaterasu may be exactly that kind of result. And there is something deeply human about this. We live on a small planet under a thin layer of air, and yet we can detect one tiny particle that crossed millions of light years, maybe more, and realize it should not be here in the way we expected. That is an extraordinary kind of awareness. It means the universe can still shock us at the smallest scale. If the answer turns out to be stronger magnetic fields, then our picture of cosmic travel changes. If the answer is ultra-heavy nuclei, then our picture of cosmic composition changes. If the answer is hidden sources in nearby galaxies, then our picture of where the universe's best accelerators live changes. Every road leads to a rewritten map. And if the final answer includes something even stranger, then the stakes rise again. Some scientists have openly said that when normal explanations fail, people begin wondering about unknown physics. That does not mean magic. It means the current set of rules may be missing a piece, and nature has found the gap before we did. This is why a single particle can matter so much. Not because it threatens Earth, it does not. The danger here is not personal safety. The danger is to our confidence that we already understand the most extreme things the universe can do. So when people say this cosmic ray came from somewhere that should not exist, they are really pointing at a deeper discomfort. The sky and the theory are not lining up cleanly. The source region looks wrong. The energy looks too high. And the path back through space may be far less simple than we once believed. That is where the story stands right now. A detector in Utah catches a tiny messenger from deep space. The messenger carries impossible-seeming energy. Its path seems to point toward emptiness. And years later, scientists are still trying to decide whether the emptiness was real or only an illusion created by the journey. So let me ask you one last thing. If you had to choose, which explanation feels most likely to you? A hidden nearby source like M82, a much heavier particle, or physics we have not fully uncovered yet? Subscribe, turn on notifications, share this with someone who loves real space mysteries, and leave your answer in the comments. Thanks for watching. I'm glad you stayed for this one. See you in the next mystery.